Okay, so we have started with the recording, and once again, Assalamu alaikum wa rahmatullahi wa barakatuh. أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم. رب اشرح لي صدري ويسر لي أمري واحلل عقدة من لساني يفقه قولي. ربي زدني علما. Yeah, so I'll just continue with the presentation. Yeah, we will see the agenda of our workshop. Okay. Mm, Last week we had seen some, I mean, last time we had seen some general aspects of process plant design, and we had seen something about deliverables, like whatever design work we do, ultimately it needs to be presented, or it needs to be documented in the form of deliverable. And we had seen some kind of deliverables what are usually made, and yeah, these are made by process engineer. Hmm? So we had seen some deliverables like BFD, PFD, PNID, process description, design basis, HNMB, OCP, startup shutdown philosophy, time philosophy, vent and drain, something about process safeguarding memorandum, uh, cause and effect diagram, alarm and trip list, line list, equipment and instrument data sheet. So we had stopped till there, and in our today's session, inshallah, we will be starting from the hazard analysis. And hazard analysis will be the last topic from the deliverables section. And the next topic would be some basic concepts which are commonly used in process plant design. Basic concepts, namely, we'll start from some basic concepts which every uh, process engineer would be expected to know, like something about a phase diagram, ideal gas law, something about pressures, something about design pressure and design temperature, line hydraulics, pump hydraulics, heat exchanger, distillation column, separator, control valve, PSU, and flares. So we plan to complete till flare. This is our plan. Let us see how much we are able to do. And inshallah, in the next week's session, we'll be covering something about simulation software, namely Aspen Hysys, and we'll also cover some topics with regards to job hunting. Uh, so till here, if anyone would like to raise any query or have any discussion, we may do. Okay, so let's continue with our next topic. And if anyone has any query in between, please feel free to stop me, and you can put forth your query. Well, so let us continue. Our next topic is heads up analysis. What is heads up analysis? Heads up analysis is basically a structured workshop, or it is a structured approach in which all the potential and hidden risks associated with the process will be identified, and it has got a very well defined structure as to how the workshop will be conducted. Ultimate aim is to identify any and all process risks. So how it is conducted, the the entire PNID of that particular process plant, it will be divided into several parts, part one, part two, part three, etc. And each of the part is called as a node. Hmm. It is actually no, and it is node can be anything. Added sometimes it can be one single line or one or two equipments, which are identical. That can be categorized into one node. For example, a distillation column, its overhead column, its reboiler can be part of one single node. Hmm. And yeah, that was about node. Then for each node, in a stepwise manner, each guide word will be defined. I mean, okay, before the guide word, each parameter will be defined. For example, parameter of flow, then we'll define a parameter with regards to pressure, then temperature, concentration, level, etc. Then we will start with for each node. Okay, we will see the parameter. I mean, we'll go through each applicable parameter. Then for each applicable parameter, we will apply each applicable guide word. No, more, less, reverse, etc. Then for each guide word, we will identify what can be the cause. I mean, why this deviation can happen. We'll see one example also so that things are a bit more clear. Yeah, so we'll also see each guide word. Then after each guide word, we'll identify what can be the cause. Then for each cause, we will also identify what can be the consequence. Like it will just lead to, say, shutdown of the plant, or it can lead to any injury or casualty, or it can lead to any explosion or any damage, any major catastrophic damage to the plant or anything else. And for avoiding this particular cause, is there any safeguard available? If yes, okay, done. If no, we give, or we means the head of team will give a particular recommendation, like, add so and so well, or, lock so and so well. Uh, to understand, let us see one example. Last time we had discussed about one PNID. Let us just go through that particular PNID. So it's not so clear, but if we can just go through this node, okay? Just consider this part of the line, the column overhead, the column vapor outlet, which goes from here and it enters into the condenser, and from there it comes into the reflux drum. So we identify, suppose this is considered as one node, okay? From the column top up to the reflux drum. Then we start by identifying the parameters, flow. Usually we start with flow. Then we start with guiders like no, less, more, etc. We start with no flow. So what can be the cause of no flow? From here to here, what can be the cause for a no flow? Say there's any valve, or operator might have accidentally closed the valve, because of which there is a no flow condition. So what can be the consequence over here? It can lead to loss in production. Hmm? And any safeguard, whatever is applicable for that particular in case. For example, one safeguard can be, the valve has been, or yeah, there's a valve, and the valve has been locked open. Like operator cannot even accidentally close the valve. I mean, that is one example. Likewise, many instances. I mean, there can be many possible deviations, many possible causes, many possible consequences. So, in this way, each of the applicable node, along with the parameter and deviation, will be assessed in detail by the HAZOP team. And yeah, this way, all the possible risks are mitigated. And yeah, the Typically, the HAZOP team will comprise of a chairman. There will be a HAZOP chairman who usually will be having an HFC and a process background. And there will be a HAZOP scribe. There should be someone to write down the points as the session goes on. Then a process engineer is also very much required since it is a detailed assessment of the PNID. Then discipline engineers would be required, namely mechanical instrumentation. In addition, it will also be other discipline engineers as applicable, like HSC, sometimes electrical, sometimes civil, and so on. Then operations team should also be there if it is a HAZOP of an existing plant, or the one who is having knowledge from operations background, or the one who is having experience in operations background, he will also be able to contribute to the HAZOP session better. So this was just in brief about a HAZOP session. We move on to the next. If anyone has any doubt, you can ask. Okay, very well. Let us move on to our next part, which is now we have completed the deliverables part. In fact, the one thing I would like to highlight here, that unlike all other deliverables which we had seen earlier, this HAZOP is not prepared by process. HAZOP is prepared by HSC, but process is the main contributor towards the HAZOP session. So let us go to our next main topic, which is on basic concepts which are commonly used in process design. Here, one of the basic things and one of the important things is on phase diagram. This is something it is essential for all process engineers to know about. Why is it so essential? Because there are many aspects of process design which, when we analyze it based on the phase diagram, it is we can understand the concept much better. So it is always essential to have this chart or this diagram firmly in mind. So, well, what is the phase diagram all about? It is a PT diagram, or a pressure versus temperature diagram, which indicates the phases of a substance. A phase diagram is something which is unique for each component. Like this is the phase diagram for water, for H2O. Phase diagram for any component, be it some gas or oil or anything, it will be almost identical with some slight changes in the shape, but it will be somewhat identical. So let us start by understanding the phase diagram of water. As we all know, that water at room or H2O at room temperature and ambient pressure or at atmospheric pressure, it exists in the liquid phase. So if we try to plot it in the diagram, it will be somewhat in over here. One atmosphere will be somewhere over here, and room temperature 25 degrees will be somewhat over here. Okay. So there are two ways to vaporize water. One is the most obvious, like we heat water and it gets converted into steam or vapor. So it moves, and at constant pressure or at atmospheric pressure, when we keep heating the water, what will happen? It was over here. My mouse is visible, right? Can you please confirm?
Yes, sir.
Okay, yeah, great. So water exists, I mean H2O under normal operating conditions exists over here. And if we heat it at atmospheric pressure, it moves from here slowly towards right. And as soon as it reaches here, this is the point corresponding to 100 degrees Celsius. So at this point, phase change will start. That is one thing, right? Like we can increase the temperature of water so that it reaches over here and it will its phase change will start. Yeah. So that is one way. Either you increase the temperature or at constant temperature, if you create vacuum conditions to some specialized equipment, if you create vacuum condition, what will happen? It was here. Now it goes here. So its phase will get changed, right? It will get converted into vapor. So there are two ways to change the phase. Either increase the temperature or decrease the pressure. So now few terms which all of us know, but just a quick recap. What is meant by melting? Change from ice into water or change of phase from solid into liquid. It is melting from here to here. Then change of phase from liquid into vapor from here to here. It is called boiling. And change of phase from vapor into liquid, it is condensation. From here to here, it is called as condensation. And change of phase from liquid into solid is called as freezing from here to here. Now, what is sublimation? Sublimation is the process in which solid directly gets converted into vapor without being converted into liquid form. So where does in this diagram where does the sublimation happen? Over here. Like if you keep going at low operating pressure, if we go over here and here, if we change the phase or if we increase the temperature or lower the pressure, we see phase change will happen from here to here. Yeah. So it's without getting converted into liquid, directly solid into vapor. So that is called as sublimation. And there is something called as a ripple point. Ripple point means three. So triple point is the point. It is a unique pressure and temperature at which all phases coexist. If we boil water, once water reaches 100 degrees Celsius, what do we see? It is partially liquid, partially vapor, right? So that is it will be somewhere over here. So that is the condition, uh, you know, um, yeah, at which two phases will coexist, will occur at the same time, liquid and vapor. Here, and if you go at this particular temperature and pressure, all three phases will coexist, and that is called as a ripple point. Uh, Ripple point for water is extremely low, at very, very low conditions of pressure and temperature. Likewise, critical point for other materials, for other liquid, for other gases, say anything, methane, benzene, carbon dioxide, H2S, etc. It might be something else. And another point is critical point. Critical point is the particular value of pressure and temperature above which no distinct liquid and gas phase exist. If anything exists over here, it will have identical properties, right? Like liquid water, its density will be around 1000 or 980 kilogram per meter cube. If it's any other liquid, oil or something else, its density will be around 700, 800, right? But if it is changed into vapor, the density falls uh, sharply. Like instead of 800 or 1000, its density will be 5, 10, 20, right? But what if it exists over here? It is called as a supercritical zone. In that, it will be neither liquid nor solid. It will be something else. And that something else is called as critical condition. And it is called as the dense phase as well, in which the properties of the fluid will be in between that of liquid and vapor. Maybe the density will not be 1000 or 800, nor it will be 520 something. It will be in between. Maybe it will be 100, 200, etc. So, yeah, that was something about phase diagram. Phase diagram, few more things continued. We have 2 more slides for phase diagram. Now, this is also something what you should keep in mind, because the topics are also used consistently in many applications. Okay, what we had seen over here, it was considering that it is just one phase, either only water or only methane or anything, but it is a pure component. What do we have? What happens if there's a mixture of 2 or more components? There will not be one single sharp line. Rather, there will be multiple lines. One line here, one line slightly above. So it will look something like this. Like anything onto the left side will be completely in the liquid phase, and anything to the right will be completely in the vapor phase, and anything in this zone will be, in this curve, anything over here will be in the 2 phase. There are 5 terms which are commonly used. Let us go through each term. First is called as a subcooled liquid. It is subcooled liquid means anything existing over here. Okay, in which it will be 100% liquid. There will not be any vapor. The vapor fraction will be 0, no vapor at all. But if we heat it up such that it reaches this curve, either we heat or we decrease the pressure, it will touch this point. And this line is called as bubble point curve. And at the bubble point curve, it is a point where the first bubble exists, or where the first bubble starts appearing. So it's like it is in the liquid form, but it starts to vaporize. So that is called as a bubble point. And here also the vapor fraction will be almost 0. Maybe it will be 0.001. What is meant by vapor fraction? Vapor fraction is the ratio of vapor to the entire fluid. Yeah. So next, if we continue to heat it further, or if we continue to decrease the pressure further, it will exist over here, and it is called as a saturated mixture. Here, liquid and vapor phases will coexist. Both will appear. It will be, the fluid will partially be in liquid form and partially it will be in vapor form. And vapor fraction will be between 0 and 1. What will happen now? Atom number 4. What will happen if we keep heating it up, or if we keep decreasing the pressure till it reaches over here? So this is called as a dew point curve. And here vapor fraction will almost be equal to 1. And here it is an ideal condition where only 1 drop of liquid is there and entire fluid has converted into vapor. There's only 1 drop of liquid. So it is called as dew point, or also called as a saturated vapor. And further, if we keep heating it further, so that it reaches somewhere over here in this zone, there will not be any liquid at all. It will be 100% vapor, and the vapor fraction will be equal to 1, and it will, it is called as a superheated vapor. And yeah, just one example. Suppose we have combination of methane and ethane. So anything existing over here will be completely in the liquid form. Anything over here to the right side of the curve will be completely in the vapor form, and anything inside over here will be in the mixed phase or two phase. So that was all about phase diagram. Anyone have any query on it? Yeah, but Nihal has some query, I believe. Go ahead, Nihal. Raise your hands. Okay. Your query was in which calculation? What I have explained you now, it is just a general thing. It is not for a specific calculation like pump, heat exchanger, etc. This is a general thing which will be applicable in the case of a pump, heat exchanger, PSC. This is, it will be applicable all rounder. Few topics what we will be seeing now. It is applicable for many different applications. And once we cover them, then we'll be going to specific equipments. Okay. Okay. So let's continue. Next is ideal gas law. This is something what we had seen since our, not just our college days, since our school days. We had seen something called as PV is equal to nRT. That is ideal gas law, and that tells that the pressure, the product of pressure and volume is equal to number of moles multiplied by the temperature multiplied by a ideal gas constant. But that is something that is an established equation, and how that equation came into picture. Let us see a quick summary of four laws which were proposed by different scientists, and it was proved on a laboratory scale. First is called as Avogadro's law, in which we know that just see over here to the top left, if the pressure and temperature is constant, and if we keep increasing the number of moles, or if we keep increasing the quantity of the gas, its volume will increase, right? So volume is directly proportional to the number of moles, or the volume is directly proportional to the quantity of gas inside the container. That is Avogadro law. And there was another scientist called as Gail Lussac. He also proposed an identical theory in which he established that for a constant number of particles in the gas and for a constant volume, if we increase the temperature, the pressure will also increase. So, in other words, pressure is directly proportional to the temperature. Yeah. Another scientist called as Charles, he established that if the number of moles and if the operating pressure is constant, uh, the volume is directly proportional to the temperature. Or if we increase the temperature, volume will also increase. And another scientist called Boyle, he established that the for a constant number of particles in the container and at a constant temperature, the pressure will be inversely proportional to the volume. If I increase the pressure, the volume will decrease. And vice versa. If I increase the volume, pressure will decrease. So the ideal gas law is a summary of all these four laws, which states that PV is equal to nRT. If suppose if I keep two things constant, if I keep volume and number of particles as constant, pressure will be directly proportional to the temperature, and so on. So this ideal gas law, basically, it provides a correlation between the pressure, volume, temperature, and quantity of a gas. If R term is constant, it always stays constant. It is called as gas constant. But one thing what we need to keep in mind is that no actual gas follows ideal gas behavior at all conditions of pressure and temperature. Now, this PV is equal to nRT. It is just one hypothetical or one ideal case, but in actual, in real life applications, all gases deviate from the ideal gas behavior. There's no real gas which exactly follows the ideal gas law. And there is a term called as compressibility. It is denoted by Z, and that is introduced to account for the non-ideality. Like this is an ideal case, like all gas, we can say somewhat follows this law, P is equal to nRT, or this is kind of a base case or skeleton structure, PV is equal to nRT. But there is another term called as compressibility. It is denoted by Z, and yeah, uh, Z is a measure which indicates how much it is deviating from ideal gas behavior. If a gas uh, perfectly follows ideal gas behavior, Z will be equal to 1. If it is not exactly following ideal gas behavior, the compressibility will be not equal to 1. Maybe it will be slightly varying. And again, the value of compressibility it varies with temperature, pressure, and composition of the gas. The ideal gas law is applicable only for gases and not applicable for liquids, as liquids are not compressible. Like how much we increase the pressure, volume will hardly change. For the gas, if the volume is, if it said 2 bar, the volume is this much. If I increase the pressure from 2 to 4, if I double the volume, if I double the pressure, volume will be half, right? It is proportional. But for the liquid, from 1 bar, if I increase the pressure to 100 bar, volume will hardly change. And that's why liquids are classified as incompressible, and liquids do not follow ideal gas behavior. Why we see this ideal gas law, and we have also seen this phase diagram, because it has got several applications. Like it will help us to understand other process engineering terms much better. Later, once we discuss about other terms, like pump and heat exchanger, column, we will come back to this ideal gas law and phase diagrams also, so that we are in a better position to understand why we discuss about these terms. Then something, okay, till here, if anyone has any doubt about ideal gas law, if anyone has any doubt, you can say, please. Okay. Let us go to next term. It is called as, uh, before we move on, let us also try to understand something about absolute and gauge pressure. This is so a basic thing, but what I saw that some process engineers are not very much clear about these terms, and that can, if we mix up absolute with gauge pressure or gauge pressure with absolute pressure, it may lead to disasters. So let us try to understand this term better. If we simply tell that the pressure, say, inside this particular vessel is 3 bar, it is not very much clear whether it is bar absolute or bar gauge. Let us try to understand these terms better. What is meant by bar absolute, or what is meant by absolute pressure? It is the actual pressure which the fluid exerts on the wall of the container. Hmm? Either it is a pressure cooker in homes, or it is a car tire, or anything else. What is the pressure being exerted on the walls of the container? It is called as absolute pressure. What is gauge pressure then? Gauge pressure is the absolute pressure minus atmospheric pressure. Let us consider few examples so that things will be more clear. Suppose I have vacuum conditions, okay, and I have some vessel which is at vacuum condition. There is nothing at all, no liquid, no gas, nothing. So, will there be any pressure exerted on the walls of the vessel? No, right? So, the absolute pressure in that case will be zero. And the gauge pressure will be the absolute pressure which is being exerted onto the walls of the vessel minus atmospheric pressure. So, atmospheric pressure is approximately 1 bar, and it is the gauge pressure will be 0 minus 1 equals minus 1. One more example. Suppose I pressurize my vessel to a pressure of 5 bar. I increase the pressure such that the fluid in the vessel, it exerts a pressure of 5 bar on the walls of the container of the vessel. So the absolute pressure will be 5, and the gauge pressure will be 5 minus atmospheric pressure will be 4 bar. One more example. At If suppose I have vessel at 1 bar absolute pressure, and at sea level, the atmospheric pressure is approximately 1 bar, hence the gauge pressure will be 0. One more example. Suppose, okay, hypothetically, if I take the vessel onto Mount Everest, where the atmospheric pressure is very low, it is around 1/3 of the pressure exerted at the sea level. So there, if I if the fluid exerts a pressure of 1 bar, the gauge pressure will be 1 bar minus atmospheric pressure, which is 0.3, which will be 0.6. So with these examples, I hope the concept of absolute and gauge pressure should be clear enough. Let me know if anyone has any query on this. Yeah, please say. It's better if you can communicate your query through, if you can say your query, it's much better. However, if you can write, that's also fine.
Yeah, sir, I have a doubt.
Yeah,
Am I
sure.
audible?
Yes, yes, you are.
Sir, if I have a reactor and in that pressure gauge, my pressure is in vacuum almost 760 mmHg or minus 1 kg. So what will be my absolute pressure?
Okay. So it is just other way around. Like absolute pressure will be gauge pressure plus atmospheric pressure. So whatever whatever is your gauge pressure, add 1 atmosphere to it, assuming that your vessel is close to sea level. So yeah, just add 1 atmosphere to it. Whatever you get, that will be the absolute pressure. Yeah.
So in vacuum, my pressure can't go below absolute pressure.
Vacuum conditions. Okay. Your pressure cannot. Yeah, that's right. In vacuum conditions, okay, the gauge pressure is almost minus one, right? Minus 1 bar gauge or close to minus 1 bar. So the absolute
Or
will always
to be
be the gauge.
accurate,
Yeah,
it's 760 mmHg. To be accurate, 760 mmHg vacuum.
yeah, yeah. Yeah, okay. So if it is 760 Hg, and that is your gauge pressure, right?
Yes.
So what you will do, okay, just to have the units clear, you will first convert it into bar. Okay, you will convert it into bar gauge. Okay, then I'm not. I'm not sure really how much it is in bar gauge, but okay, whatever value you get in bar gauge, okay, 760 mmHg. Suppose you convert it into bar gauge, you get value of X. You have X bar gauge, okay. So the absolute pressure will be X plus 1 atmosphere. So absolute pressure is always greater than the gauge pressure.
Okay.
Okay. So we move on. Okay. Before we start the topic on design pressure and design temperature, let us go few slides back. Last time we had seen about this deliverable called as process safeguarding memorandum, in which we had seen about the levels of safety or ultimate safeguard. We had seen that the inherent safety for any process plant is the design pressure and design temperature. Suppose we had seen an example, a fluid is operating at a pressure of 8 bar, okay, at say 8 bar gauge. The design pressure, suppose it is 12 bar gauge. So the 8 is the maximum operating pressure. The design pressure is 12. So that margin of 4 bar on top of the operating pressure is called as the design pressure, right? Likewise is the case of a design temperature. Suppose my fluid is operating at a temperature of 70 degrees Celsius. I have a design temperature of 90. Maximum operating is 70. I have design temperature of 90. So that excess 20 degrees Celsius margin is called as a design temperature. Hmm? So the question is, how do we calculate, or based on what do we define the define the design conditions? So there are some guidelines to it, which we will be seeing now. Uh, okay, before I go through this, let me just be clear on it that these are some indicative guidelines, based on some codes and some codes, and in fact, this is based on ad hoc codes. And for case to case, of from company to company and from application to application, it may slightly vary. There are few exceptional cases to these guidelines, but these are the general things what you can keep in mind. Okay, so we see that uh, okay, first we need to establish what will be the maximum operating pressure and temperature in all possible operating scenarios. Hmm. Suppose I have three operating conditions. We can operate the plant in this way, in this way, and in this way. And in this way, my operating pressure is 6. In this way, if I operate, my operating pressure is 8 bar gauge. Here, my operating pressure is 9 bar gauge. So 6, 8, and 9. That there can be three different cases. So I see out of the three, 6, 8, and 9, which case has the highest operating pressure. So 6, 8, 9. 9 is the highest, right? So I choose 9, and on top of 9, I define some margin over it. So let us see where does 9 comes in this table. 9 is over here, right, between 0 and 10. So if 9 is my maximum operating pressure, my design pressure will be 9 plus 1 equal to 10. So design pressure in this case will be 10 bar gauge. So what do I mean by minimum design pressure and maximum design pressure? Like maximum, the equipment or the vessel or the pipe should be such that it can withstand a pressure of maximum 10 bar gauge, or at least for 10 bar gauge, the thickness or the pipe should be designed such that up to 10 it can withstand, and also it should be able to withstand a pressure of -1 bar gauge, or in terms of bar absolute, it will be zero bar absolute. Okay. Likewise, suppose if my maximum operating pressure is 80 bar gauge, then uh, for a 80 bar gauge, it should be the design pressure will be 80 multiplied by 1.05 or add a 5% margin on 80. So it will be 84. Yeah, that's how this table works. Now, obviously, it has got few exceptional cases, like for, say, for a distillation column, for an atmospheric storage tank. This table is not valid. There are some other conditions to it, and those conditions are actually beyond the scope of today's workshop. For more details, you can refer to API codes, API 520, API 521 can be referred if you wish to look into it in more detail. That was about design pressure. Now let us look about design temperature. What is design temperature? It is maximum or what value for design temperature should I choose? Whatever is the maximum operating temperature, add a 15 degrees Celsius margin to it. Suppose if my maximum operating temperature is 100 degrees Celsius, the design temperature or the temperature what the particular vessel should withstand should be 100 plus 15, which should be 115 degrees Celsius. For any vessel or for any pipe which is exposed to sun, its design temperature should not be less than 85 degrees Celsius. This is also one standard. You know, suppose I know that this particular vessel which I have designed, it will not operate at more than 10 degrees Celsius. However, I cannot choose or I cannot specify a design temperature less than 85 degrees Celsius. Minimum 85 degrees Celsius it has to withstand. However, if the vessel or if the pipe is buried, if it is underground, such that it is not exposed to solar radiation, then this 85 degrees Celsius minimum criteria can be relaxed. It is okay to have a design temperature less than 85. And whatever I get, whatever final design temperature I get, it is usually rounded off to the next higher multiple of 5. Suppose I have a design temperature, or if I have a maximum operating temperature of 102 degrees Celsius, design temperature would be 102 plus 15, which will be 117 degrees Celsius. So I round it off to the next highest 5. So if the design temperature, what I have established, it is 117, I'll just round it off to 120. Now, whatever we discuss now about the design temperature, it is about maximum design temperature. There's another term called as minimum design temperature. The design temperature, same as the design pressure, it has got two limits, upper limit and lower limit. Upper limit means the design temperature should not exceed, the actual temperature must not exceed a particular value. So it is the called as maximum design temperature. Similarly, it should not go below a particular limit, and that it should not go below a particular limit is called as minimum design temperature. So the minimum design temperature should be either of the two. Either it should be, mm, it should be either the operating temperature, what is the minimum operating temperature, minus 10 degrees Celsius. Okay. Suppose I know that my vessel will not operate below 10 degrees Celsius. So the design temperature should be 10 minus 10 equal to 0. It should be designed such that the vessel should be able to withstand up to 0 degrees Celsius. Or it should be equal to minimum inner wall temperature resulting from a depressurization minus 3 degrees Celsius. Okay, what is this? Let us look something about minimum inner wall temperature resulting from depressurization. If I depressurize my vessel, if I force the gas, there's a vessel, the gas passes out of the vessel, through a narrow opening, and across the narrow opening, or called as a choke, or it is called as valve. Once the gas will pass from the narrow opening, its temperature will drop, right? So, based on the composition, whatever is the temperature drop expected, -3 degrees Celsius. So that, whichever is the lowest, either this or this, whichever is the lowest, that should be specified as my minimum design temperature. So here, anyone have any doubt till here?
Why this minimum design pressure is -1 bar gauge only for all these cases?
Okay, good question. Thank you. Uh, no, there will be, most conditions in a process plant, it is expected that vacuum conditions will be created. Why vacuum will be created? Anything can happen, ranging from, suppose the vessel, once it is purged, okay, I mean, because of during maintenance, the vessel, it will be subjected to steam, right? For cleaning, we use steam. We will pass steam through the vessel, and once we pass steam, and once steam will condense, its pressure will tend to fall. It will tend to go into vacuum conditions. Not complete vacuum, but partial vacuum will be created. That is one example. Second example, there is, if the vessel is filled with gas, and if the gas condenses, the condensation of gas, it will also create a partial vacuum, or due to any process conditions, there will be chance of vacuum. It is expected that, even though normally that particular vessel operates at 1 bar gauge, but because of anything, the pressure may go negative, or it may go below atmospheric pressure. Like three examples I gave, likewise there can be many examples or many cases in which the pressure may go below atmospheric pressure. Because of this, we usually define it as, -1. Like, we define that minimum design pressure should be -1. But there can be some exceptional cases in which, during the design phase, we know for sure that there cannot be any operating case in which pressure goes below atmospheric pressure. In those cases, it is allowed to have a minimum design pressure of higher than, -1. It can be 0, it can be -0.5. Yeah. 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 So, let us go to the next topic of line hydraulics. Yeah, till now we had seen about some general concepts like design pressure, design temperature, absolute gauge pressure, ideal gas law, phase diagrams. These were some general concepts. Now we will see some specific concepts. Something about line hydraulics. Then we will see something about pumps, heat exchanger, and all. I think let us complete the topic of line hydraulics before our break. Line hydraulics. If anyone would have attended any interview for the role of a process engineer, he might agree with me that one of the first question which the interviewer will ask is about line hydraulics. I mean, I had given interview in uh, many places in my entire career, and I have seen this thing that one of the basic questions or one of the starting questions will be on line hydraulics. The question is, why is line hydraulics considered very basic and very important? Fluid uh, needs to keep moving in the plant, right? From one equipment to another equipment, from one plant to another plant. Inside a pipe, it has to move from one place to another. So fluid cannot move from one place to another place without a difference in head. Yeah, the study or the analysis of the difference in head, it is covered under line hydraulics. That is why it is considered as most basic and quite important. Fluid cannot move from one place to another at all without a difference in the head. So the principle when you see about line hydraulics is that a head gradient is required to push a fluid in a particular direction. You know, if fluid moves from higher elevation to a lower elevation, fluid moves from here to here. It is because this point is at a higher head than this point, right? That's why fluid moves from here to here. Likewise, if fluid needs to move from one particular point to another point, it is essential that this is at a higher uh, pressure compared to this point. Only then the fluid will be able to move from one point to another, right? So yeah, all this analysis, it comes under uh, line hydraulics. So when we speak about line hydraulics, let us see some concepts like exactly what do we aim to calculate with line hydraulics. When I say that I'm doing a line hydraulics calculation, my aim are these. I need to calculate the line size. Either the line should be for a particular desired amount of flow. What should be my line size? Should it be 6 inch, 2 inch, 8 inch, etc.? So that is, I need to calculate the line size. Yeah? And another objective of line hydraulics is to ensure that velocity and pressure drop are within allowable limits. There will be some velocity of fluid which will pass of the fluid which passes through the pipe, and there will be some particular pressure drop. So it is to ensure, or by doing line hydraulics, I am able to calculate what will be the velocity and what will be the pressure drop of the fluid which will pass through the pipe. What inputs do I need to give for doing a line sizing calculation? I need to start with a tentative line size. I know that line size might be something else, but I will start with a tentative line size. So I start with 6 inch. Then after doing the calculation, I got to know not 6 inch is not enough. I need a 8 inch. Or alternatively, I start with a line size of 6 inch. And after doing the calculations, I get to know that 6 inch is too much, not really required. I can have 4 inch also. So that is the difference. Like we start with a tentative line size and we get a final line size. And obviously we also need to define the flow rate, what will be the pressure and temperature, what will be the density, viscosity, compressibility, specific heat ratio, etc. I need to define these terms, and I need based on this, I will get the outlet pressure, pressure gradient, pressure drop. What is the pressure drop occurring in the line? What is the velocity? What is the final line size? What I will get? You know, this is about basically about line size and what are the allowable limits. Now again, this chart, what is shown over here, it is just for an indicative purpose, but the actual line size will, sorry, no, the actual limit, it varies from company to company. Maybe some company in UAE might have slightly different allowable limit than a company in US or in India. Oh, but yeah, it is almost identical. So let us consider one or two examples. Suppose I have a liquid which is going to the pump. Okay, I have a liquid which goes from a storage tank into the pump, and it is highly volatile liquid. What do I mean by highly volatile liquid? Let us go to the phase diagram again to know, because this volatile, whether the liquid is volatile or not, you know, this is something what will be regularly used in process engineering based discussions. Basically, any liquid, any fluid operating which is in the liquid phase, but it is operating at very close to its close to vapor condition. So it is called volatile. Normally, oil, it is classified as volatile liquid. But water, when it exists at ambient temperature, 25-30 degrees Celsius, it is not a volatile liquid. So water will be somewhere over here. But anything operating close to the two-phase zone, it is called classified as volatile liquid. So when we come to line hydraulics, there are separate criteria for volatile liquid and a non-volatile liquid, or any liquid which is operating close to its bubble point, or any liquid which is at the subcooled condition, which is too far away from the vapor case. So there are two different terms. There are two different criteria. Let us see each of them. Suppose I have water, okay, and I start with calculation for a water line. There is water line connected from the storage tank to the pump, okay, and I got to know that the line size for that particular water line is 8 inch, and I see that at 8 inch, what is the velocity and pressure drop criteria? Suppose after doing the calculation, I see that the velocity of water passing through the line, it is 1.1 meter per second. Is it within the criteria? No, right? Actual velocity is 1.1, but allowable as per the criteria uh, is 0.9. No, sorry. Since I was speaking about water, water is not classified as volatile. It is subcooled, you know. So at 8 inch size, uh, if I have velocity of 1.1, it is acceptable. It falls over here, so that 8 inch is fine. But what if suppose I need to pass petrol from or any other oil, which is close to its bubble point. If I need to pass that oil from a storage tank into a pump, and I find that velocity is 1.1, is 1.1 greater than 0.9? Yes, right? So that means that I will have to increase the line size from 8 inch to the next highest size, which will be 10 inch, so that velocity comes down, and I need to keep going down till velocity and pressure drop are within allowable criteria. So that's how we use this table. My line size must not be so high that velocity is 0.1 or 0.2, so it will lead to other corrosion issues, or it will unnecessarily it will increase my cost of the pipe so much. I need this much pipe, but I'm using this much pipe, so that is also not advisable. Likewise, all the velocity and pressure drop should be within allowable limits. So for each particular process conditions, there will be one optimal pipe size. So we need to calculate that optimal pipe size through line hydraulics. Line hydraulics is governed by some equations. Let us have a quick brief through on the equations to have a feel on what is exactly going on behind the scenes. Why I say behind the scenes? Because most of the cases in any process design activity, we never use this equation directly. I mean, these equations are already inbuilt in some software like Aspen Hysys, or in some in-house Excel sheets, or in some in-house calculation sheets. So these equations are inbuilt already. We just need to define some values of flow, pressure, temperature, etc., etc. We'll get the line size. But what equations are actually used to calculate the line size? Let us have a walk through on those equations. First thing is velocity. We saw that we will start with a tentative line size, right? That based on the flow rate and based on the tentative diameter, we will calculate velocity. Then there's another term called as Reynolds number, which we will calculate based on velocity and diameter, as well as density and viscosity. Then based on the Reynolds number, we'll calculate the F value. F is the friction factor of the pipe, of the fluid in the pipe. And F will be calculated through an iterative approach. We'll assume some value of F and we'll get the final value of F. When I say assume some value of F, suppose I don't know the value of F, I will start with a value of 0.5, suppose. And once I calculate it, I get a value of 0.7. 0.5 has given me 0.7. Then again, I use the same equation, and with the same equation, I get a value of 0.65. Then again, I calculate, I get 0.67. Then I get 0.66. Then after that, how many times I calculate, I will get 0.66. So it is an iterative approach. Value is this. Initially, I start with this. After each calculation, I'll get a different value until it will converge and it will stop at this value. So that is called iterative approach. With the iterative approach, I'll calculate value of F. And with the value of F, I will calculate the pressure drop. Then again, I will judge whether velocity and pressure drop are within acceptable limits or not. If yes, okay, stop. If no, I find that pressure drop and velocity is too high. I can't have this. I mean, based on this chart, I find that velocity and pressure drop is too high. What will I do? I will increase the line size so that velocity will come down and pressure drop will come down. So that is how an iterative approach is used to calculate the pressure drop. So that was about line hydraulics. And before we start on pump hydraulics, let me know if anyone has any query.
In
Yes.
many cases, we saw that some line sizing are done by a velocity basis only. Okay, and so in other industry, it will be done on pressure drop basis. So my question is that when we consider on velocity basis line size and when we consider on pressure drop.
Okay. See, basically, unless specified otherwise, we need to consider both the bases, like velocity and the pressure drop basis. But if we see over here, if we see in this chart, we see that there are some instances where only velocity criteria will be defined. There will not be any pressure drop criteria defined, such as the last part of the table, service water, seawater. There's only velocity criteria defined. There's no pressure drop criteria. So here we'll only use velocity criteria. We will not use the pressure drop. Why? Because pressure drop in some cases does not really make a difference. It is the velocity which makes a difference. And most cases it happens that if velocity criteria is within limits, pressure drop criteria will automatically be within the limit. We don't even have to check. Sometimes it happens that way.
Excuse me, sir.
Yeah, please say.
Sir, this line sizing is only applicable or feasible when we are designing it for a pump, or we can do it on current parameters.
It says, okay, you mean to say that I understand by your question that only when we do the design of a pump line, then only line sizing, I mean, line hydraulics has to be used. Is that your question?
Yes, and one more thing, because if I am doing it for if only I am changing my pump and my system is old, or I think it's 5 or 6 year old. So can we? What am I having the issue is that basically the pipe roughness and the friction factor basically.
Yeah. Yeah. Okay. Let me answer you. It is not that it is line hydraulics is used only for pumps. You know, be it any line going into vessel or any pipeline which is going from one plant to another plant, if it is coming from a height, for any type of line hydraulics has to be performed, not only for
Yes,
pump lines. Second
yeah,
thing,
but
yeah,
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 but if we are not having the changing the setup, so we have to use the same. And for that, we have to again calculate the length, the thickness, and the main is the friction factor. So and it get varies due to the roughness of the pipes.
yeah, this is the true. Okay, let me answer this way. First
And
of all, yeah,
due to the scaling due to the scaling, the pipe roughness gets increased. Now there is more pressure drop, more friction factor.
okay. You see that line hydraulics is mostly it is applicable for new lines. If any new line has to
Okay,
be built, if any new line has to be designed or any new line has to be built, well, based on my line hydraulics, I will calculate or I'll establish the line size, you know, whatever, 2 inch, 8 inch, 10 inch, etc. So mostly applicable for the new lines, but even for existing line, for an existing pipe or for an existing plant which is already in operation, you know, for that also line hydraulics is sometimes performed just to check adequacy. It is performed to ensure whether I'm having a 8-inch line, my flow is 100. Is that 100 really? I mean, can my pipe actually withstand 100? And usually it will be
okay,
only for information purpose, because the plant is already built. Usually, we won't demolish that line and bring a new line, you know, unless it is really required. Whatever it is, we will be like, "Kaam ko chala do abhi." So, but yeah, sometimes if we find that really line hydraulics is creating an issue, we will perform line hydraulic calculations on an existing plant and whatever required actions we take. Suppose uh, through an 8-inch line, my flow is 100. Okay, based on line hydraulics calculation, I find that 100 is actually too much. My line cannot really withstand 100. So what do? I change the flow to 90, or I will adjust other parameters to suit that particular line size. Or if really it is creating issues and I find that my line size is not adequate, sometimes in plants they consider removing that line and reinstalling it with a higher line size. That is also done. So yeah, basically line hydraulics is performed for mostly for new plants and sometimes for existing plants also. Got it?
okay, okay. And one more question.
Yeah.
So can I use the same pressure drop calculation for designing a PD pump?
Yeah. Line hydraulics is not for any only for a particular category of pump. It is general for all pumps, for all compressors as well. Line hydraulics is performed. Yeah.
So, but because of the viscosity, we get very high pressure drop.
Because of the viscosity, okay, pressure drop will be very high. Okay, so accordingly, the line size may vary, like depending on the viscosity. Like suppose if my viscosity is too high, my the, the Reynolds number and F value will vary, and accordingly the pressure drop will also vary. And according to the high viscosity, the applicable or the allowable limits will also vary. But in general, yeah, line hydraulics has to be performed. Either velocity is low, I mean viscosity, if it is low or high, but line hydraulics is to be performed to calculate the optimal line size. Okay, and the question was, please explain about two-phase line sizing. Uh, Okay, now what I had explained over here, this equation for the pressure drop and equation for the F value, it is applicable, it is a general equation, it is applicable for liquids. But if it is vapor, if it is vapor, or if it is a two-phase, these equations will vary. How it will vary? There are separate equations given in separate codes. Okay, one of the most commonly used codes is API 12, no, sorry, API 14E. You can just refer to those codes for a detailed calculation of F value and pressure drop. It is explained in those codes like API 14E. Likewise, other relevant codes are also there. But what is explained over here, it is some only some general equations. Even for gases and for two-phase flow, the equation usually it is very long. It is not there this much. Maybe it will be in two lines, maybe. But yeah, it revolves around this equation itself, what is explained over here. Detailed analysis of two-phase is actually beyond the scope of our current workshop, actually. And in yeah, when you asked about two-phase, there is one more thing we need to know, that in two-phase there will be different cases, you know, depending on what kind of phases are there, uh, and how much is the combination of liquid and how much is the combination of gas. There will tend to be different issues, like one is called as a slug flow. Sometimes it will go into dense phase and so on. So yeah, it is something bit more complex than this, but yeah, it basically uh, eh, okay. All I can say is revolves around these equations, but the equation will not exactly be the same. Yeah,
Okay, thank you.
yeah, you're welcome. Now, since we are somewhat halfway through, let us take a break for say for 15 minutes. Okay, so we'll be back after 15 minutes, inshallah. So by 10:20 UAE time or 11:50 India time, we'll be back. Okay. Yeah, yeah, yes, sir. Sir,
Alaikum.
Walaikum salam warahmatullahi wabarakatuh.
Sorry, brother. Actually, getting stuck
Alhamdulillah, fine.
even in weekends, so did not able to actually attend. So
Okay, okay.
apologies for this. And mashallah, tabarakallah. Thank you very much, for your continued efforts. Though I see there are not really good participations. But yes, thank you very much. So that even, these recordings also, inshallah, would help guys.
Inshallah.
And,
Yeah, yeah.
and the presentations, right? So please keep doing the best work. Inshallah, whatever support is required, always available. Inshallah. Okay. So
For
please
sure, inshallah.
keep continue, please.
Yeah, inshallah. Jazakallah khairan. We just
Right.
started with a short break. If you can, after the break, if you can be there for some time, a quick introduction or a quick speech from yourself, it will be appreciable.
Yeah. So how many guys were there this morning?
Roughly roughly six were there. 6 7 people were there.
Okay.
So
So
they called for
what
the break.
what time you are joining back?
We'll join back at 10:20, inshallah.
Right. Inshallah. Okay. I'll join back. Inshallah.
Yeah.
Okay. I'll try to
Okay,
join.
inshallah.
Okay.
Yeah, sure.
Shukran. Thank you.
Welcome. Assalamu alaikum warahmatullah. Whether sir yet to join. Hello sir, Farhad bhai. Assalamu alaikum.
Salam. Everybody join back?
Not yet.
Okay.
Few more are yet to join.
Okay.
All those who are here at the moment, Noor and Rawa. So far, if you have any query on what we discussed, we can make use of this time to discuss it till the time others join.
Thank you, Amir. Okay.
So, Sasad bhai, I think so. Since we are running out of time. Let us start. And okay, so although there are not many people yet, but uh, yeah, I would also like to thank our admin of our Kokni Engineer Association group, who is with us at the moment. So, Jazakallahu khairan, Safaz bhai. It has been a pleasure to have you here, and he has ensured that we are aligned on group, and thank you for it. I mean, your inspiration and your commitment actually helped me to to start this workshop last year and this year as well.
Ji, Assalamu alaikum warahmatullahi wabarakatuh. Definitely, Umair. I mean, it's not just about a person, right? It's about our responsibilities. Once we become into any professional life, we should give it back to our community, and that's what actually we are following, right? And we are encouraging others as well. So thank you very much. Really appreciate it for your initiatives. I keep asking our expertise. We do have, mashallah, like 1,000, around 1,500 professionals, but very few are coming up front, and they are like dedicating their time and to ready to share their knowledge. So thank you very much. You are one of them, always ahead in the queue to share your knowledge. So that really, I mean, makes very much valuable for our community, and we hope to continue such this process where inshallah few more also will join and will share their knowledge. So whenever whatever help and support is required, we are available in the group, as well as you can do any of our member, they can send a PM, and inshallah we'll do our best whatever we can. Okay. So without further ado, I know we are in very important session, so let us please continue, and please let us know if anything can be done from my end. So thank you very much for attending all. by sparing your precious time. And believe me, I mean, this is gonna be really, I mean, added value to your profile, to your whole career, actually. So what I would suggest is, please convey the message to your friends, your colleagues, and I know there are like tens of dozens of your friends are there in our group. So please encourage them to participate and share with them that what you are learning and what they can gain from such workshops. So thank you again for your giving the time to the community and to yourself. So thank you very much. Jazakallah khair. And I will take yes, thank you very much. I really appreciated Umair and all others attending this precious workshop. Yeah.
For the kind words. Yeah, let's continue with the workshop. Although it would have been much better that all those who were there before the break, all of them would have been with us now. It would have been better, but yeah, considering time constraints, let us continue from where we stopped. We had seen about line hydraulics. Now our next topic would be on pump hydraulics. Before I start on pump hydraulics, which forms one of the basic basic items of process engineering design. I would like to give a few examples so that things are more clear to us, on why exactly we need a pump, what a pump does, like hydraulically, what does a pump do? We will see something about it. Okay, the basic principle for a pump is to create a head gradient artificially, in order to push the fluid in the required direction. In which the moving impeller of the pump creates a high velocity, which turns into pressure energy. We'll look into details of this definition, but before that, let us consider a few examples. Just consider case of electricity. Okay, let us slightly deviate from our topic and consider an example of electricity. Electric current, as we know, that it always moves from a higher potential. It moves from a higher voltage or higher electric potential to a lower electric potential, right? It never happens other way around. I mean, it usually, or under natural conditions, it will not happen other way around. Likewise, for the heat transfer, heat will always transfer from hot to cold, not from cold to hot, right? Likewise, mass transfer, mass will always get transferred from an area of higher concentration to a lower concentration. Likewise, for a fluid, fluid will always move from an area of higher head to a lower head. I mean, these are the general things what naturally occur. Now let us see the other side of the coin. Normally, electric current, as we have seen, falls from higher voltage to lower voltage. But if we want to force it from lower voltage to higher voltage, we need a battery. Yeah. Likewise, for the heat transfer, normally happens from hot to cold. If we transfer heat from cold to hot, we will need a heat pump application, right? Likewise, for a mass transfer, always happens from high concentration to lower concentration. If we want it to happen in other way around, low to high concentration, we will need something artificially, like reverse osmosis process or something, right? Likewise, for the head, normally fluid moves from higher head to lower head. But what if fluid has to be forced from lower head to higher head? We will need to artificially create a head gradient so that fluid is able to move from low head region to higher head region. And that work is done by means of a pump. So that is what pump does. It ensures that fluid will move from a region of lower head to higher head. Head can be anything, either from a low elevation to a higher elevation, or it can move in a straight line. No, normally fluid cannot move unless there is a head difference. And if head difference is not there, it can be artificially created by using a pump. And that is what the pump actually does. No? It forces fluid it absorbs electrical energy, and that electrical energy is converted into some mechanical energy, because of which fluid is moved from the low head region to higher head region. Yeah. Now, how it does it? Now, although there are several different kinds of pump, the most commonly used pump is a centrifugal pump, about which we will be seeing now. What happens basically? The impeller of the pump keeps moving at a very high speed, right? When a fluid enters into the suction of the pump, a high velocity is created, and as the fluid moves into the discharge of the pump, that high velocity or high kinetic energy of the fluid or of the liquid is converted into pressure energy, because of which high pressure is created. That is about pump. And now we will see, like, when we do a pump hydraulic calculation, what are the objectives? Like, mainly, what do we want to calculate by doing a pump hydraulic calculation? Mainly two things. There might be other things as well, but mainly it is about these two things when it comes to process design. One is differential pressure required across the pump will be calculated. At the pump, I have a suction pressure of, say, 5 bar. At the discharge, I do some calculations. This is my pump. I know that because of certain things before the pump, or at the suction of the pump, the pressure at the suction nozzle is 5 bar. And I do my discharge line hydraulics, discharge vessel calculations, based on which I know that at the discharge of the pump, pressure of 20 bar will be required. 5 at the suction, 20 at the discharge. So the differential pressure which needs to be induced, or differential pressure which needs to be created artificially across the pump, will be 20 minus 5 equal to 15 bar. So that is what my pump hydraulics do. Another thing is to ensure that MPSH-A is greater than MPSH-R. Okay, what is MPSH? That we'll see in detail. Now, just keep in mind that MPSH available should be greater than MPSH required. When we do any pump hydraulics, what are the key inputs what we need to define? We need to define conditions like flow rate, pressure, temperature, density, viscosity, vapor pressure, etc. Then what is the suction and the discharge line size, 2 inch, 4 inch, 10 inch, etc. And what is the length? And okay, what is the elevation and operating pressure of suction and discharge tanks? My pump is here, suction tank is here or here or here. What is the elevation? And in the suction and in the discharge tank, or in the suction and discharge vessel, what is the operating pressure? What is the elevation? These things needs to be defined. And what output do I get in the pump hydraulics? At the pump, what is at the suction nozzle? What is the pump? I mean, what is the pressure? At the discharge of the pump, what is the pressure? And across the pump, discharge minus suction, what is the differential pressure, or what pressure needs to be created across the pump? These are the things what need to be calculated. Now, likewise, there's MPSH-A. What is the MPSH available across the pump? And what is the power being consumed by the pump? These are the key outputs which are calculated or which are established in a pump hydraulics calculation. Next is the pump performance curve. for any centrifugal pump, there will be some curve which will be defined by the manufacturer of the pump. Uh, One of them is called as a head curve. Like it gives the head curve gives a measure of the head on the y-axis versus flow on the x-axis. So it basically it gives a measure. Let's concentrate on this head curve. Like it gives a measure of if how much is my flow, and with the flow how much my head will vary. And there's something called as efficiency curve. If higher my flow, higher will be efficiency. But after the particular limit, efficiency will keep reducing. That is about efficiency. Then there's the power curve, which gives measure of how much power the pump will consume at what flow. Suppose at a peak flow of 100, it will consume very high power. At low flow, it will consume lower power, and so on. There's something called as an NPSHR. Okay, we'll see it in the next slide. So this curve will be given by the manufacturer, by the vendor, based on the flow rate and head range, which is defined by the process engineer. Being a process engineer, suppose I define that I need a pump, the minimum flow should be 100, maximum flow should be 200, and the head requirement should be 100 meter. So, yeah, based on the specification or based on what I specify, the pump vendor will define his curves, or the pump vendor will provide me with the curves based on my inputs. And based on the available curves, I need to see which is the best, which curve will best fit my operating region. That is how a pump hydraulics is done staged wise. Now let us see about some equations, about some example which will allow us to understand this better, inshallah. The pressure generated across the pump, like, okay, we saw that the objective of the pump hydraulics is to calculate the differential pressure across the pump. What should be my differential pressure, or what pressure the pump should create? Yeah. So that is given by this. That is given by the okay, basically by this equation. It is a it varies on 4 things. 1, 2, 3, 4. Yeah. And it is a addition, or it is a summation of 4 things. One thing being the elevation difference between the discharge and the suction tank. Suppose my suction tank is over here, my discharge tank is over here. There's a small difference between the discharge and the suction. What if my discharge tank is moved to a much higher elevation? So the difference will be more, right? So the pump will have to create more pressure in order to ensure that required amount of flow reaches till the top. So one of the thing, or one of the term, is elevation difference. Second is the pressure difference between the discharge and the suction tank. Suppose the suction tank is open to atmosphere, where the pressure will be 0 bar, okay, and the discharge tank is at say it is going into a pressurized vessel where the pressure will be 5 bar. So it needs to create a specific amount of head, right? The pump has to artificially create some pressure, because of which fluid is able to pass from 0 bar to 5 bar. What do you think will happen if the discharge tank pressure is increased? Not 5 bar, it is increased to 10 bar. So the pump will have to create more pressure, or it will have to create more head in order to ensure that liquid reaches till the top. Yeah. So that is another term. It also depends on the pressure difference between the suction and the discharge tanks. Third term is line loss. If I water friction or whatever pressure losses occur across the pipe, I will have to minus that pressure, or not really minus. It will have to be added up. Suppose I have a line size of say 4 inch, 4-inch line size, and it creates a particular pressure drop. What do you think will happen if I decrease the line size? Not 4-inch, I decrease it to 2-inch. There will be very high velocity and very high pressure drop across the line, right? So because of that, very high velocity and very high pressure drop across the line, the pump will have to create a higher pressure in order to overcome the pressure losses. And fourth thing is there will be a control valve at the usually at the discharge of the pump. So if the control valve is sized such that it has a very high pressure drop, the pump will have to create more pressure. So yeah, these are four things based on which the pump differential head will vary, will depend on. Till here, anyone has any query?
Actually, not in this, but I have one
Yeah.
query. For example, we calculate means one pump NPSH, okay, and if it's come for example 40 meter. So when we purchase this pump for our plant, okay, for our brownfield project, so is it any thumb rule or any some values which we need to add means more we want more head required?
Okay.
So,
Very soon. Yeah, sorry. That's what I'm saying, that very soon I'll be answering that question, because I have not yet covered the topic of NPS. Once I cover the topic of NPS, then we'll come back to this question.
okay.
Okay, so let us move on to the topic of NPSH of a pump. What is NPSH of a pump? NPSH basically stands for net positive suction head. What is the effective head at the suction of the pump? It is a measure of the head across the pump, or the pressure of the pump. Higher the pressure, higher will be the NPSH available. Lower the pressure, lower will be the NPSH available. And to understand the concept of NPSH better, let me just go back to the phase diagram, what we have discussed earlier. When a pump or when fluid moves from a tank or vessel into a pump, it will initially in the tank, it will be somewhere over here. Okay, you can see my mouse, right? So usually the temperature of the fluid will continue to remain constant. So that means that initially it was here, and the temperature being constant, and because of the friction in the pipe, the pressure of the fluid continues to fall down. Initially it was here, the pressure has come down, because of pressure drop occurring across the pipe. It will start coming down, will come over here, and there will tend to be a point when at constant temperature, the fluid will tend to vaporize. When I say vaporize, not completely, but bubbles will start appearing if the fluid moves over here, if the fluid will touch this zone, bubbles will start appearing. And bubbles, if it starts appearing, it might create a disastrous damage to the pump. If it happens for a very short instant of time, usually it is okay. But if it continues to happen for hours and days, then in very short time, the pump can be damaged because the pump cannot withstand bubbles occurring in the pump. Yeah? So initially it was here, and because of pressure drop occurring across the suction line, it will start coming down, and if it touches over here, it can cause damage. And that is what NPSH is all about. NPSH calculation ensures that by the time fluid moves into the pump, it continues to be in the liquid phase and it does not touch the boundary point. That is basically what NPSH is, or NPSH calculation is all about. Now, there are two terms called as the NPSH available and NPSH required. The NPSH available is the actual head, or it's the actual pressure which occurs at the suction of the pump. NPSH required is the pressure, or it is the head what is required at the suction of the pump as defined by the manufacturer of the pump. Suppose manufacturer defines that at the suction of the pump for that particular flow rate, the NPSH required is 2 meter. And in actual, I'm getting an NPSH available of 1.5 meter. Means that whatever will be the head, or whatever will be the pressure, that particular pump at that flow rate will not withstand that condition of pressure. And that is what can damage the pump. So basically, it should be ensured that NPSH A should be greater than NPSH R. That is one of the two objectives of a pump hydraulics. Now, how do we calculate the value of NPSH available? NPSH available depends on these 4 things. One of them is the pressure of the suction vessel, or it is the pressure from which fluid comes into. Okay, that is one of the terms. The second term is the head difference between the tank and the pump. This is basically if the pump is here, tank is over here, or if the tank is moved to a higher elevation, H value will be higher, and it is good for my NPSH. I will get more NPSH by the time fluid comes into the pump. So high, and whatever will be the pressure drop, pressure loss across the suction line of the pump from the storage tank to the pump, that is this delta P suction. If the suction line is too small, or if velocity is so high that it creates so much pressure drop across the suction line, my NPSH available can go below NPSH required and it can damage the pump. So lower the suction line loss, the better will be the NPSH available value. And lastly, fourth term is about vapor pressure across the vapor pressure of the fluid at that operating temperature. So if the vapor pressure is too high, it might create a low NPSH available, and that may again lead to cavitational damage at the pump. Now, this is one thing what many of us would have come across. I have personally come across this issue in one of my previous companies, in which they were having issues with the NPSH. Like, what do you do when ideally, it should be ensured that MPSHA is greater than MPSHR. Okay, but what do you do if you find that MPSHA is not greater than MPSHR? You know that there can be cavitation and damage across the pump. Yeah, but what do you do in order to mitigate it? This equation for NPSH will provide answers to this question. Whatever is most economically and technically viable, we do that. The fluid come, yeah, sorry. Any question?
No. Okay.
So basically, if a fluid comes from a tank into a pump, uh, the tank, the vessel will have some pressure, right? Or okay, if it is open to atmosphere, there will not be any pressure. But if it is not open to atmosphere, there will be some pressure. So if possible, we can increase the pressure of fluid in the vessel. If my fluid was at a pressure of 3 bar, and if it is increased to 5 bar, it will have a positive impact on my NPSH value. Likewise, if I increase the elevation difference, pump is here, vessel is here. If it is possible, I can increase the elevation of the vessel. If it was at 2-meter elevation, I can increase it to 4-meter elevation. Or if the pump was at grade level, I can dig a hole in the ground and I can put the pump in the trench. Another possible way to increase the NPSH. With regards to the suction line, if my line size is 4-inch, and if I increase it to 6-inch or to 8-inch, it will have a positive impact on my NPSH available. Since pressure drop will come down, the NPSH available will increase. Likewise, I can also decrease my vapor pressure by altering the fluid temperature, if possible. So yeah, that was about NPSH. Now there's one more thing. This called as an NPSH curve. Like NPSH available is calculated based on this equation, and NPSH required is calculated based on this curve, which is provided by the vendor. At so and so flow rate, suppose at 100 flow, my NPSH is this much. If I increase the flow, I will need a much higher NPSH. But at each condition of flow, my NPSH available should be greater than NPSH R. That is what is the curve is all about. So, Noor, you have any additional questions to this with regards to NPSH?
Actually, sir, my previous question is about differential head. Okay, if I calculate the differential head is for example 40 meters. Okay,
Okay,
and
fine.
I put this value in my calculation. Okay, while purchasing the pump, is it any thumb rule that will compensate the gaps between the calculations and the actual field value? Means in
Yeah.
brownfield. In brownfield, the every means walls and bends are not as per our standard sizes. They are differences. That's why I'm asking.
Mm, Uh, okay, so always there, whatever we calculate and whatever we purchase or whatever actually happens on site, there will usually be some gap. No, it will not exactly be the same. Gap might vary. Sometimes 1-2% gap, sometimes 5-10% gap. So what we do in order to overcome or in order to compensate for the difference between what we calculate and what we or what happens in site in actual. Mm, First of all, some margin will be considered uh, on the flow rate. Suppose I have a flow of 100 and my maximum flow is 100. But for sake of my pump hydraulics, I won't consider 100. I will consider some margin on top of 100. Maybe I will design the pump for a flow of 110 or 105. So that 105 or 110 is the additional margin. That is one of the thing. And yeah, that is one of the thing which will compensate for the difference between what is calculated and what happens in actual. Second thing, most of the cases, after the discharge of the pump, as you can see over here, there's a control valve in place. Yeah. So across the control valve, there will be some pressure which will be dropped. Yeah. So suppose we have done some calculation in which the differential pressure across the pump will be 40 meter. Okay. Differential pressure will be 40 meter, and the control valve pressure drop will be, say, 1 bar. But in actual, when I purchase the pump, when I install it, construct, commission and all, I find that the differential pressure across the pump is not 40 meter, it has to be 42 meter. So how do I bring that extra 2 meter into picture? I lower the pressure drop across the control valve. So the control valve will usually compensate for the slight inaccuracies in the calculation. Clear? No?
Oh, okay. Thank you.
Let us move on to our next topic. We have seen about line hydraulics. We have seen about pump hydraulics. Next, we go to the topic of heat exchanger. In a heat exchanger, basically what happens? Heat gets transferred from hot side to cold side through conduction by virtue of temperature difference. I have a fluid, I have hot fluid which needs to be cooled, and I have a cold fluid which needs to be heated up. So I pass both the fluid, the hot fluid and the cold fluid, in a heat exchanger, so that heat gets exchanged, heat gets transferred through convection and conduction, and without any actual mixing of the fluids, only the heat gets transferred from hot to cold. Yeah, that is basically what a heat exchanger does. When we do the calculation for the heat exchanger, what is the main objective? The main objective is to calculate the heat exchanger area and the geometry required to achieve the required temperature gradient. That is my main objective. If I have a hot fluid, suppose its flow is 100 and cold side is 80, and hot side temperature falls from 100 to 70, cold side temperature increases from 30 to 40 degrees Celsius. So to achieve that, for that required flow and for that operating conditions and for that required heat transfer, how much area would I require? And what will be the geometry of the heat exchanger? Like how many tubes will be required? How many tube passes will be required? So these kind of things are calculated through heat exchanger sizing. Here, the main inputs for my heat exchanger, or the main input for my heat exchanger calculation, will be the flow rate, pressure, inlet temperature, outlet temperature, density, viscosity, heat capacity. Then what is the heat exchanger type? Whether it is a double pipe, or whether it is a shell and tube, or whether it is a plate and frame, or anything else. Then is the hot side, suppose if I take a shell and tube heat exchanger, is the hot side on the shell side, or the hot fluid is on the cold side? I mean the hot fluid, is it on the shell side or it is on the tube side? So these are the key inputs which needs to be defined from a heat exchanger calculation. What is the output I get from a heat exchanger calculation? I will get an output of what is the heat transfer area required, what is the number of tubes, what is the number of shells, and how many tube passes are required. You know, Mm, then what is the second side flow and what is the second side temperature? What is meant the second side fluid? Okay, second side flow. Sometimes it is for the heat exchanger calculation, my main fluid, its flow will be defined. Suppose I need to heat oil using steam. So I know my flow of oil. Oil is flowing at 150 meter cube per hour, suppose. What flow of steam would I require? Whether flow will be 50, 70, 80, etc. So that I get based on heat exchanger calculation. And once steam will heat up my oil, what will be the steam inlet temperature? I had an inlet temperature available, and what will be the outlet temperature of steam? Once it will transfer heat to my oil, what will be the outlet temperature? And what will be the pressure drop across the heat exchanger? So these are the key outputs what we get from heat exchanger calculation. That was just a quick overview of heat exchanger calculation. Now we see some equations which govern or which form the basis for heat exchanger calculation. You know, as we know from the law of conservation of energy, that energy can neither be created nor be destroyed. It can only be transferred from one form to another. Yeah. So similar is the case for a heat exchanger. What in an ideal heat exchanger, whatever heat is lost by the hot fluid is absorbed by the cold fluid. Heat lost by the hot fluid is given by this equation, and heat absorbed by the cold fluid is given by this equation. Now, what are these terms? Let us see. Uh, yeah, the heat lost by the hot fluid is governed by three terms. One is mass flow rate. Second is specific heat capacity of the fluid. Specific heat capacity means how much heat do I need to give in order to increase the temperature of 1 kg of the fluid by 1 degree Celsius. Heat capacity of water is 4.2. Okay, it is 4.2. Okay, kilojoule per kg per degree Celsius. So what is meant by it? If I have 1 kg of water, and if I want to increase the temperature of 1 kg of water by 1 degree Celsius, how much heat will be required? So that is the specific heat capacity of that fluid, and that is given by Cp. Now, delta T is the temperature difference or temperature drop uh, through the heat across the heat exchanger. Temperature was 80 at the inlet. At the outlet, suppose it got decreased to 60. So 80 minus 60 equal to 20 is the temperature drop across the heat exchanger. So that is given by this delta T term. So whatever is the product of these three terms, mass flow rate, specific heat capacity, and temperature difference of hot fluid will be equal to mass flow rate multiplied by specific heat capacity multiplied by temperature difference cold fluid. So if any one of them is unknown, based on other terms, we can calculate it. So yeah, that is explained by this term. And by this term, which is Q is equal to U into A into delta T Lm. With this term, or with this equation, I can calculate the heat transfer area required. How? Value of Q is the heat exchange between the hot side and the cold side. And Q is equal to this thing, this M into Cp into delta T hot is equal to MCP delta T cold. And this is actually the value of Q. And value of Q is equal to U. U is the overall overall temperature difference, or sorry, it is the overall heat transfer coefficient, and A is the area required, and delta T Lm is the logarithmic mean temperature difference. Let us look into these terms one by one. Q, or the heat exchange between hot and cold, we know it can be calculated from this equation. Value of U, usually it is available in literature, based on what is the hot fluid and what is the cold fluid. Some approximations are available, and it can also be calculated by using some equations. Okay, they're beyond the scope of this workshop, but yeah, there are some equations based on which value of U can be calculated. And delta T Lm. What is delta T Lm? Let us try to understand it based on this this graph or this chart. Suppose I have a hot fluid and a cold fluid. It passes through a heat exchanger. Through the heat exchanger, the energy from the hot fluid gets transferred to the cold fluid and keeps passing until it comes out of the heat exchanger. Okay. So the initially temperature difference, suppose hot fluid was at 80 degree, cold fluid was at 40 degree. And at the end, hot fluid comes down to 60, and the temperature of cold fluid increases up to 55 degree. So initially, the temperature difference was 80 minus 40 equal to 40. And at the end, the temperature difference is 60 minus 55 equal to 5. So the temperature difference between hot and cold side, it was 40 initially. It started decreasing. The temperature difference between hot and cold started to decrease. Initially 40, 39, 38, 37, 36, 35, and so on. It decreases up to 5. So what is the mean of all this? That is what delta T Lm gives. Logarithmic mean temperature difference. So area of the, what will be the area required for the heat exchanger? What is the heat transfer area? Whether it is 100 square meter, 1 square meter, 10 square meter, etc. It is governed by this equation. Now again, value of overall the logarithmic mean temperature difference, it varies based on whether it is co-current or counter current. What is meant by co-current? Suppose my heat exchanger is this, okay? Yeah, the hot comes from here, cold comes from here, and hot leaves from here, cold leaves from here. So the inlet of both the hot and cold are same. I mean, are at the same side. Outlet are at the same side. So that is co-current. But if my hot is here and cold side is flowing from opposite direction, so hot enters here, exits from here. Cold opposite, enters here, exits here. So it's opposite, right? So that is counter current. So there are several differences between co-current and counter current. Considering time constraints, we'll see one example of why counter current is sometimes better than co-current. Suppose my hot side temperature is 80 and I need to cool it down, and my cold side temperature will be 40. So there is no way that I can achieve a cold side outlet temperature greater than hot side outlet temperature, right? Because fluid I mean, heat gets transferred from hot to cold, right? And if the temperature is same, there will not be any heat exchange, right? So the basically outlet temperatures cannot cross. Hmm. There's no way outlet temperature can go below the outlet temperature of cold side. But in a counter current, it will be possible. Why? Because suppose it was 80 here, it has come down to 55 for my hot side, and for my cold side, the inlet temperature was 40, and by the time fluid comes into the hot side inlet, my hot side inlet is still hotter than the cold side outlet. So there is still possibility for heat transfer from hot to cold. So ultimately, the outlet temperature of hot fluid can be lower than outlet temperature of the cold fluid. And that is the key advantage of counter current over co-current. That was the end of heat exchanger. If anyone has any query with regards to heat exchanger, we can discuss on it.
If you have some notes regarding heat exchanger sizing, uh, please share with us heat exchanger sizing related
Sure, sure.
notes.
Yeah, sure. In fact, I have one very good book. So I'll just mention that book. Later, I'll just share that group. I'll share the book in our group. So it explains very good about a heat exchanger, separator, column, and all. And I had learned heat exchanger concept in that book itself. So inshallah, I'll just share that book. Okay. Okay. Let us move on to our next topic, which is about a distillation column. You know, distillation. When we talk about distillation column, it is it it is about all about the separation of two or more components by virtue of difference in boiling points. You know, suppose I have a mixture of ethanol and water. Okay, ethanol boils at a temperature of roughly 70 degrees Celsius. Water boils at a temperature of 100 degrees Celsius. What will happen if I take mixture of water at what will happen if I take a mixture of ethanol and water, and if I heat it to a temperature of between their boiling points. Ethanol boiling point is 70, water boiling point is 100. What will happen if I heat the mixture to 85 degrees Celsius? Almost all ethanol will vaporize, water will continue to stay inside, right? So that is how the two mixtures will be separated out. Ethanol went up because its boiling point is less. Water continued to stay because it still has not boiled. So it will continue to stay here. Now, just consider this arrangement, what is shown over here, where I have okay, here it is shown as salt. Right. Suppose if it is ethanol and water, and if I heat it to a temperature of 85, once again, ethanol boils at 70, water boils at 100 degrees Celsius. If I heat it to 85 degrees Celsius, what will have happened? Ethanol will evaporate, and suppose it is not open to atmosphere, it is a closed vessel. So what will happen? Ethanol will evaporate, but it will condense back. It will condense back, and it will be almost pure ethanol over here and pure water over here. That is about a batch distillation process. Now, okay, consider Okay, now let us go to this continuous distillation process. Uh, Here, what happened? The fluid, the hot fluid, continuously flows. Okay, not hot, can be anything, hot or cold, but yeah, there's a continuous flow of fluid, you know, and liquid will fall down. Like whatever is liquid, it will fall down, and the distillation column will be maintained at a temperature which is in between the temperature or which is in between the boiling point of both the fluid. Meaning, suppose same example, I have a mixture of ethanol and water. Okay, ethanol's boiling point is 70 degrees Celsius, water is 100 degrees Celsius. If I maintain the distillation column at a temperature in between 70 and 100, water will continue to come down and ethanol will continue to come up. Now, ethanol which has come up, it will not be pure ethanol. There will be some water carry over with the ethanol. Likewise, when water has come down, it will not be pure water. There will be some ethanol which has got carried away with the water and it has come down. So in order to increase the purity, some of the some of the ethanol will be sent back such that we get a more pure ethanol finally at the distillate. Likewise, some water will be sent back into the column so that we get a better purity of water in the final bottoms product. And that is what a distillation column is all about. Now, in any distillation column, we will be having several stages. It's called as plates or trays or stages. There will be one plate over here, second plate here, third plate here, fourth, etc. Likewise, if you come down, there will be plates. Why are the plates for? Or why is it divided into stages? To understand this better, let us go back to our batch distillation example. I had a mixture of ethanol and water. Okay, suppose it will be 50% ethanol and 50% water. Once I do the distillation and ethanol moves up and it condenses into another flask, it will not be pure ethanol. There will be some water carryover along with ethanol. And in the initial vessel, on the initial stage, I had a 50% ethanol and balance 50% was water. Okay. Here, suppose I get 90% ethanol, 10% is water. Suppose I transfer that 90% ethanol and 10% water into another identical arrangement, and we do the same heating process again, because of which in the new arrangement, from 90% ethanol has come to be 98%. So again, if I repeat it in a third arrangement or in a third vessel, from 98%, the purity will come to 99.5%. Yeah. Initially, it was 50% ethanol. Once I do the distillation, it came out to be 90%. Then 90% came out to be 98%. Then 99.5, and so on. That is why we have different stages in the distillation column. As we move up to each stage, at each stage, the concentration of ethanol or the lower boiling point fluid will increase. And likewise, if we go down, the concentration of the higher boiling or the concentration of fluid having higher boiling point will increase. As we go up, ethanol is more. As we go down, water is more. That is basically about what distillation column. And when we do the design of a distillation column, the objective is to size the column. We need to and it's auxiliary. We need to calculate what must be the size of the column, what must be the diameter, what must be the height, 2 meter, 10 meter, 100 meter, anything else. Yeah. And how many trays must be there? What should be the reflux ratio? What should be the spacing between each tray? Those things have to be established. What are the inputs? The key inputs when we size a distillation column are flow rate, pressure, temperature, properties of of all the components, and what purity of distillate and bottoms are required. In general, if we want a very high purity product, I don't want a 99%. I want it to be 99.999% pure. Suppose. So accordingly, it can be done, but the column size will increase. So higher the purity, higher will be the column size. And what will be the heating and cooling mediums? Once the once the vapor has come out, it needs to be condensed back, and for achieving better purity, part of the condensed product will be sent back into the column. So what utility do I need? Do I need a refrigeration? Do I need refrigeration, or do I need cooling water, or anything else? What is the cooling medium? Likewise, what is the heating medium? Do I need to use a heater, fired heater, or do I need to use steam or anything else? What is the heating medium? And what is the boiling point of distillate and bottoms? In this example which I gave, the boiling point of boiling point of the distillate was 70 degrees Celsius, and boiling point of the bottoms product is 100 degrees. Likewise, the output what I will get from the column sizing is the size of the column, how much tall, and how much should be the diameter, and what will be the size of the reflux drum required, what will be the heat duty, how much heat do I need to give at the reboiler, and how much heat do I need to extract from the condenser, and what will be the reflux rate, how much needs to be sent back into the column, and how many stages are required, what is the operating pressure in of the column. So these are the main outputs what I will get from the column from the column sizing calculations. With regards to distillation column, there are a few more things to add. I mean, one example what I will give, we might have very much heard about vacuum distillation. Why distillation is performed under vacuum conditions? Sometimes it happens that I need to separate out two or more oils. Suppose I have crude oil, which needs to be distilled, and my heavier component has a boiling point of say 400 degrees Celsius. Okay, and my other components have boiling point of 200, 300, etc. But the heavier one boils at 400 degrees Celsius. Okay, so if I want to separate out the heavier ones from the other, if I there's another component which is boiling at 350 degrees Celsius, another component which boils at 400 degrees Celsius, right? So if I need to separate them out, I will need to have a temperature of between 350 and 400. So that is very high temperature, first of all, I will need a very high thermal energy. No, my energy cost will increase if I need to go till that very high temperature. Secondly, there are chances that at high temperature, some chemical reactions called as cracking would occur. If I were to heat the oil to a that much high temperature, if I heat it to a temperature of 380, 390 degrees Celsius, my oil will start to crack. The heavier oils, it will crack and it will get converted into low molecular weight oils. So I don't want that to happen. So what do I do? I bring down the operating pressure by creating a vacuum, okay, such that it can be that the distillation can take place at a lower uh, temperature. Suppose let us go into the concept of phase diagram, which we had seen earlier. My component was boiling at a okay. Suppose it was boiling at a temperature of say 400 degrees Celsius. Okay, so at 400 and at atmospheric pressure, it was boiling. What do I do if I need to decrease the boiling point? I don't want it to boil here. I want it to boil at this temperature. I bring down the pressure. And how do I bring down the pressure? By creating a vacuum. So that after I created vacuum or after I created partial vacuum, the fluid will not boil at this temperature. Rather, it will boil at a reduced temperature, because of which my cracking reaction will not happen now. I mean, that is the explanation why sometimes a vacuum distillation will be used. So, if till now, since we are already out of time, let us pause here. And if anyone has any query, we can discuss on it. And beyond this topic, other topics, inshallah, we will cover it in our next week's workshop. So till here, you have any query? Noor or Lawan?
Same thing, Umer bhai, for distillation also. If you have any means calculations procedure for distillation column with example, if you have, please share with us.
Sure, sure. I will, inshallah. Mm. In fact, okay, the book which I had told about, inshallah, I'll be sharing that book in our group, and it is very nice book for heat exchanger, especially for heat exchanger and distillation column. It is explained in so much detail. And along with some examples, it has been explained. So once you go through them, it will be even clear, because due to time constraints, I had just explained the whole view of a column and a heat exchanger. But once you look into that, you will be you'll be in a position to understand it much better. So before we end the session, we'll just see what all we need to cover in our next topic in our next week workshop. One will be about the separators, then control valves, PSV, flare. And then we will see about some simulation software, and then we'll go into the job hunt topics. So inshallah, next week we'll be winding up this workshop. Once again, thank you so much for attending, and inshallah we'll see you in the next workshop, which will be
Okay, Jazakallah.
next week Sunday, inshallah. Okay. Assalamualaikum warahmatullahi wabarakatuh.